Hey Extension 2, welcome back to your next video lesson. We're going to kick off today with a flashback HSC question from 2006. 3 quick 1-mark questions. Hit pause on the video and see how you go figuring them out. Okay, for question I, we have to find z squared. So we're going to square 3 plus I using a perfect square expansion, of course. So we have 3 squared. Multiply them together and double it, and then we have I squared. And of course, from last lesson, we know that I squared is equal to minus 1. So we have 9 minus 1 gets us 8 plus 6i. 1 mark if you got it. Okay, for part 2, we're doing the conjugate of z multiplied by w. So for z conjugate, we take the imaginary part and we change the sign. And now we do a binomial expansion. So we get 6 minus 15i, multiplying the 3, and then we get minus 2i, and then we get plus 5i squared. Okay, 2 negatives make a positive, and we have 5i squared. 5i squared is of course minus 5, so we have 6 minus 5 is 1, and minus 15i, take away 2i, is minus 17i. Okay, and for the last part, this part's a little bit trickier. We did these in the last lesson. We're doing w over z as a fraction, and we want to write it in the form x plus iy. Okay, this means we need to realize the denominator, which means we're going to multiply top and bottom by the conjugate of the denominator, which again is 3 minus I. Okay, on the top, we've got w times z conjugate, which we already did in part 2, so we have the answer for the top. On the bottom, we can do a difference of 2 squares. So 1 minus 17i was our answer from part 2, and we've got 9 take away I squared. I squared is of course minus 1, so we have 10 on the bottom, and then we're going to split it apart and have 1 over 10 as our real part, and we're going to have minus 17 over 10 as our imaginary part, because the question said we want an x plus iy. Okay, so you need to split apart your fractions if you want to make sure you're not going to lose any silly marks. Okay, excellent. On to today's lesson, which is on the geometry of complex numbers. So last week's lesson was more about the algebra of complex numbers. Today we're going to look at making pretty pictures all around complex numbers. So let's talk about how we can construct a sort of complex number plane. We're going to talk about the geometry of what I is doing to a number. So we're going to start off with the number 1, shown here on a number line as like a sort of vector from 0 to 1. Now, of course, if I multiply or divide this by negative 1, the result is negative 1, of course. I'm going to show this by turning the arrow around to face the other direction. Okay, remember, positive and negative are just directions. So another way we can think of this as, instead of turning the arrow around, we can think of it as a rotation. So let's say, just for argument's sake, that multiplying by negative 1 rotates this arrow around anti-clockwise by 180 degrees. And let's say that dividing by negative 1 rotates us clockwise by 180 degrees. Okay. Now that we have a rotation, now we can start to ask questions like, well, if negative 1 is a whole rotation, how would you be able to find half a rotation? And to answer a question like that, you need something that's multiplying twice that gives you an answer of negative 1. So it's almost like you need the square root of negative 1, which in complex numbers we can achieve. Okay, so if multiplying by negative 1 rotates us 180 degrees, that must mean that multiplying by I is a 90-degree rotation, because times I is I squared, which is negative 1. Okay? So from this, we can start to see an extra axis of numbers coming using these complex numbers. So if we think of I as a 90-degree rotation, well, now we have a set of real numbers going across the x-axis, and we have a new vertical axis showing our imaginary numbers. And this is where we get what's called the complex plane. Okay, we have the horizontal axis as our real numbers and our vertical axis as our imaginary numbers. Okay, we graph this stuff on what's called an Argand diagram. So we're going to graph the complex number z equals x plus iy as the coordinate x, y. Okay, that's partially why we chose x and y as our 2 letters, because it corresponds to a coordinate in the Cartesian plane. So here's our Argand diagram. We have x as our real axis and y as our imaginary axis. So this point right here, this has a real value of 3 and an imaginary value of 2. So this point here corresponds to the complex number 3 plus 2i. 3 on the reals and 2 on the imaginaries. Okay? Another way we can represent this number geometrically is instead of a point, we could instead use a vector. Okay? Now, a vector is technically defined as anything that has a direction and a magnitude. So we could say that this complex number, 3 plus 2i, also corresponds to this line, which has this length going in this direction. Okay? Vectors is a topic that you will be exploring in Extension 1, either at the end of this term or the start of next term. So once you've covered that in more depth in Extension 1, these concepts will make a lot more sense in Extension 2. So the two courses do complement each other really nicely. Okay? This notation here, when I have what's called a tilde, T-I-L-D-E, underneath a letter, this means that Z is a vector. Okay, so vector Z, 3 plus 2i, this red guy right here. Okay, this green dot right here, this is actually our complex number Z multiplied by I. And let's have a look. So we take our Z, we multiply everything by I, so we get 3i and we get 2i squared. 2i squared is negative 2, so our new complex number after multiplying by I is minus 2 for the reals and positive 3 for the imaginary axis, which is this point right here. So here's what's happening algebraically. Geometrically, we can see what we were looking at in the warm-up, where we're taking this red line and we are rotating it by 90 degrees in the anti-clockwise direction. Okay, so multiplying a complex number by I rotates the vector by 90 degrees, or pi over 2 radians if you prefer, in the anti-clockwise direction. Okay, very important. So that point there is IZ. Some more points, this one down here in orange, this is actually Z multiplied by -1. So we'll see this algebraically. We'll take our number, we'll make the 3 negative, we'll make the imaginary part negative, and so now we are 3 to the left and 2 down. Okay, we can see this geometrically as the red line turning around, as we saw in the startup, okay? Or another way you can think of this is multiplying by I, and then multiplying by I again is multiplying by -1. So it all works. Illuminati confirmed. Okay, over on the right here, one more point in purple. This is actually the same complex number as Z, except the imaginary part has changed from 2 to -2. So this must be the conjugate. Okay, so Z conjugate, we're changing the 2 to a -2. All this does geometrically is it reflects the point across the real axis. Okay, so a complex number and its conjugate will be reflections across the real axis. Okay, cool beans. Let's talk a little bit more about vectors. This is probably the more complicated part of this lesson, but like I said, once you've done some more Extension 2, you will feel more comfortable, I promise you. So right here we have a vector representing the complex number 2 plus 2i. The reason I know that is because it's pointing to the point 2 plus 2i. Now here's where things get a little bit tricky. We say in mathematics or in physics that two vectors are equal if they have the same direction and the same magnitude. Doesn't matter where they are, okay? So this green vector and this blue vector are actually the same because they have the same, they're parallel, they have the same direction, and they have the same length, okay? So this green vector over here on the left, this actually also represents the complex number 2 plus 2i, even though it's not pointing at the complex number 2 plus 2i, okay? It's only going to point to its complex coordinate if you're starting from the origin, okay? So this right here is called a position vector because it's starting from the origin. This one out here is called a free vector, but they both represent the same complex number, which is a bit of a strange concept at first, but you'll see why this works a bit later on. Okay, so we're going to look at some more geometry of doing some addition and subtraction of complex numbers. So here we have a complex number, 1 plus 2i. Here is its vector. It's starting from the origin, so it points to the coordinate 1, 2. Here is another vector represented by w. This complex number is -3 and I. So it's 3 in the negative direction and 1 in the imaginary positive direction. Okay, now what we're going to do is we're going to take z and w and we're going to add them together. So here is z plus w. We're going to add the real parts together and get -2. We're going to add the imaginary parts together and we'll get positive 3i. So let's see where that point is. It's right here. Okay, so here is z, here is w, and this point here is z plus w. Let's have a look at why this happens. When you add two vectors together, it's kind of like you're doing them both one after the other. Okay, what I mean here is we're going to travel along vector w, and then we'll travel along z, and where we end up is z plus w. Or we could have gone the other way. We could have started at z, traveled along, then we could have traveled along w, and then we end up at the same point. Okay, because remember, w could be right here, or we could move it just here, and it's still the same vector. Okay. The way my brain made sense of this when I was first learning it is I just said, well, w and z are already making half of a parallelogram. If you finish the parallelogram, the other corner will be the sum z plus w. Okay, so this vector right here, or this point right here, both represent z plus w, which is minus 2 plus 3i. Okay, so adding two vectors together, you are completing the parallelogram. That's the way I call it, completing the parallelogram. Okay, now let's look at what happens geometrically when we subtract the two vectors, which is a little bit trickier. So we're going to do z take away w, starting with z, subtracting w. So we'll have 1 plus 3 is 4, and we'll have 2 minus 1 is 1, so we have just positive 1i. Okay, the point 4 plus I is 4 across and 1 up, so it's just here. Okay, now this vector here is z minus w, and the geometric relationship between z, w, and z minus w is that z minus w is the exact same as the vector from w to z. Okay, so the vector from w to z, if we put it down starting at the origin, it's going to point to the complex number z minus w. Okay, so what we're going to remember is that if you want to find the vector z minus w, geometrically, all you got to do is a vector from w to z. Okay, it's kind of like we're working backwards. Z minus w is w to z. I'm going to say that a few times this lesson so it sinks in. Okay, so there's our geometric relationships. Let's do a few practice questions to try and get a bit more comfortable. So here we have a complex plane, courtesy of Howard Mathematics. We have a point z and a point w. We're going to sketch all these transformations, and I'll put a bunch of axes in your booklet so you have plenty of room to write on. Okay, I encourage you to pause the video and see how many of these you can remember based on the last couple of minutes. The ones you're not sure about, just leave and I'll go through with you right now. Okay, first of all, iz. We said before that multiplying a complex number by I is going to rotate it 90 degrees or pi over 2 radians in the anti-clockwise direction. So if this is z, 90 degree rotation gets us I times z. For question B, we're doing the conjugate of w. We said the conjugate is swapping the sign on the imaginary part. So instead of being up here on the imaginary axis, we're going to be down here. And so we said that reflects us across the real axis. So here is w, reflected across is w conjugate. For question C, we're going to do negative w. So we're going to take w and we're going to reflect it through the origin. So it's kind of like we're rotating 90 degrees and then rotating 90 degrees again. Okay, so the imaginary part is swapping sign, and so is the real part. So right here is negative w. The vector just turns around and points the other direction. For question D, we're looking at 2z. So we're going to take the length of the vector z from the origin, and we're just going to double it. So here is z. We're going to double the real component, and we're going to double the imaginary component. And so right here is z doubled, or 2z. Okay, for E, we are going to sum the two complex numbers together. So we're going to draw a couple of vectors, and then we're going to, like we did before, we're going to complete the parallelogram, finish off the other two sides, and this corner right here is going to be z plus w. Or you can think of it as we're doing z and then w, or we're doing w and then z, whatever works for you, okay? Okay, question F, we're going to do z minus w. So the shortcut we said is you do a vector from w to z. Okay, so from w to z, from here to here, we'll place this vector down at the origin, and then it points to our point, which is z minus w. Okay, so that point right there is not z minus w, that's z. You've got to move the vector down, starting at the origin, and then it points to your complex number. Okay, up next for question G, we have a pretty similar question. This time instead of z minus w, which was the vector from w to z, now we're going to do w minus z, which is the vector from z to w. Okay, so this red line is going to turn around, and then we're dividing it by 2, which means we're going to cut the length in half. Okay, so here is our w minus z, okay, from z to w. We'll put it down starting at the origin, and then we'll cut the length in half, and there is our w minus z divided by 2. Okay, for our last one, we have a couple of transformations to make. So we're doing z conjugate, and then we are multiplying it by minus I. Okay, so first things first, we'll take z and we'll do the conjugate, which reflects across the real axis. So this here is z, this red dot will be z conjugate. Now, multiplying by I rotates us 90 degrees anti-clockwise, like we saw before. However, if you're multiplying by negative I, you're going to rotate 90 degrees in the clockwise direction. Okay, so this green line here is z reflected across the real axis and then rotated by 90 degrees. All right, so we've got z here, and imagine there's a negative there, and I didn't stuff up because I don't want to re-record. So this is negative IZ. Okay, up next for example 2, we have a square OABC, and point A represents the complex number 2 plus I, so 2 across and 1 up. Okay, first part is probably the most challenging part. It's a bit of a strange question. Let W represent the complex number at C. So this is Z here, and W is just here. Show that Z squared plus W squared is equal to 0. All right, so we've got Z here and we've got W here. So to form an equation relating Z and W, we need some information that relates the two. So what can you say about Z and W? Maybe think about these vectors Z and W. What relationship can you see here? Well, we know because it's a square that these two vectors are the same length. So the length of Z will be the same as the length of W. We also know that because it's a square, this is a 90-degree angle right here, which means that W is a 90-degree rotation from Z. What this tells us is that W is just Z multiplied by I, as we saw previously. Okay, so now we have an equation relating W and Z. But we want an equation relating Z squared and W squared. So let's take our equation and let's square both sides. Left-hand side, we get W squared. Right-hand side, we get I squared Z squared. And of course, I squared is -1, correct. All right, so we have negative Z squared on the right-hand side. Now, what do you know? We can bring it across and we add them together and we get 0. So we get Z squared positive plus W squared equals 0. Now, a very important part of Extension 2 Maths is that when you are asked to prove something and you successfully prove it, after your proof, you write QED. This is a Latin acronym that stands for Quod Erat Demonstrandum. It's basically a translation for what was to be shown. It's kind of like you saying, you asked me to prove this, and look, I proved it. Sucked in, I'm smarter than you. Okay, so just a nice way of sticking your thumb up at your marker and saying, I beat you, I'm better than you. Really, really good feeling, trust me. Okay, part B, find the complex numbers represented by B and C. So we have the complex number A, we've got 2 plus I. We're gonna figure out what C is, and then we're gonna figure out what B is. If you think you've already got an idea, please pause and have a go. So to find C, as we saw in part A, well, the complex number C is just A multiplied by I. So that's what we'll do. We're gonna do C equals I times Z. So we're taking our 2 plus I, we're multiplying it by I, so we get 2I plus I squared. So we end up with -1 plus 2I is the point right there. Okay, coolly. So we have the point A and we have the point C. How are we going to use these 2 points or these 2 vectors to figure out the point B? If you're thinking vector addition, you are on the right track. So we've got this vector here for C, we've got the vector here for A. If we add the 2 vectors, we're going to complete the quadrilateral and we're going to get the corner point B. Okay, so B is just A and C plus together. So we're going to do 2 plus I for the point A. Got the point C. If we add them together, we get 1 for the real part and we get 3I for the imaginary part. Okay, cool. So the geometry and the algebra are matching up. This is good to know. Now for part C, find the complex number represented by the vector AC. So we've got another new bit of notation here. This right here means the vector, so the arrow on top tells you it's a vector, the vector from A to C. All right, so the vector from A to C. If you remember from previously, we said if you want to find a vector between 2 points, you do a subtraction and you kind of work backwards. Okay, so the vector AC can be found by doing the point C, take away the point A. Okay. All right, so point C is minus 1 plus 2i. We got that from before. Point A is 2 plus I. We had that from the question. If we subtract them, we're going to get minus 3 on the real part, and we'll get 3 on the imaginary part. So that's C minus A, so that's from A to C. If we put this vector down at the origin, it'd be pointing to minus 3, 3. Okay, groovy. Up next, a similar question with a little bit more of a challenging twist. We have ABCD is another square in the complex plane. The vertices A and B represent the complex numbers 9 plus I and 4 plus 13i. Find the complex numbers corresponding to, first of all, the vector from A to B, and then the vertex D. Okay, let's work through it together. And by together, I mean I'm going to talk to my computer. All right, so vector AB, the way we find this, like from before, we can do point B, take away point A. Okay, from A to B is B minus A. You got to try and train your brain to work backwards for these ones. Let's make some space. All right, sweet. So AB is B minus A. So if we take the coordinate B, subtract the coordinate A, or the complex number A, we're going to have 4 plus 13i, take away 9 plus I. 4 minus 9 gets us minus 5, and 13 minus I gets us 12i. Okay, so there we go. That vector right there is represented by the complex number minus 5 plus 12i. Okay, it doesn't mean that this vector is pointing to the point minus 5, 12i. It's currently pointing to B. If we wanted to point to the complex number minus 5 plus 12, we have to move it starting from the origin. Okay, so this point right here would be minus 5, 12i. Okay, now question B. Find the vertex D. So how are we going to use this vector to get the complex number D? Hopefully, once again, you're recognizing that we have a 90-degree rotation because conveniently, once again, we have a square, and that's good. So if we take this vector right here from A to B, if we rotate it by 90 degrees, it's going to be pointing from A to D. Okay? So the way we're going to do that is we'll take our complex number, minus 5 plus 12i. So we'll take this vector, and we're going to multiply it by I. Okay, so we're going to do minus 5 plus 12i. That's going to get us this blue vector here, and then we're going to do some clever maths to shift it across and up. So it's here, and that's going to be pointing to the point D. Okay, so first things first, we'll take minus 5 plus 12i. We'll multiply it by I. So we get minus 5i plus 12i squared. That turns into minus 12, and so we have minus 12 minus 5i. Okay, so minus 12 minus 5i is going to be this point just here, which is not what we want because we want the vertex just here. Okay, so it's almost like we don't want this blue vector to be starting from the origin. We want it to be starting from point A. All right, so the way we're going to do that is we're going to take this vector, which is minus 12 plus, minus 5i. We're going to shift it across by 9 units, and we're going to shift it up by I units. Okay, then the blue vector will be positioned here, and it'll be pointing towards the point we need, which is D. Okay, so we found this vector, we put it at the origin, we rotate it, and then we move it back across, and we have our point D. Okay, it's absolute witchcraft. So we take our point D, we're adding 9 plus I. We end up with minus 3 minus 4i. Okay, adding the reals, adding the imaginaries. That right there is the coordinate of point D, minus 3 minus 4. Okay, hectic. We'll pump the brakes a bit here. We're going to look at a HSC question from 2009. It's a pretty easy, simple 3-mark question. Encourage you to pause the video and see if you can quickly get these 3 marks correct. See how you go. They're a band 2 to 3 question. Okay, if you've been paying attention, you know that for question I, to find IZ, we take the vector from the origin and we rotate it by 90 degrees. So this is going to be point R representing IZ. For part 2, if we want the conjugate of Q, we just need to reflect it across the real axis. So if this is Q, this is going to be S representing W conjugate. And then for part 3, to add the 2 vectors together, as we've done a couple of times now, we just complete the parallelogram, complete the quadrilateral, and there is point T, which is P plus Q, which is Z plus W. Okay, sweet. Hopefully you got 3 out of 3 for that one, and you're ready for a couple of more challenging questions to finish off the video. So here is a challenge question. We'll be doing more questions of this style later in the year, but I just thought this was a cool question I wanted to show you guys. So right here we have a complex number Z. We have 1 divided by Z, take away 1 divided by Z conjugate is equal to I. Now the question is stating that this is actually an equation of a circle, and it wants us to prove it or show that. Okay, so we need to try and make this look like a circle. So I'll give you guys a starting point, and then if you're feeling confident, you can pause and see if you can get the algebra to work. So if we're trying to find the equation of a circle, we need a relationship between x and y. So the smartest thing we can do first is, instead of having z and z conjugate here, we'll make this x plus iy, and we'll make this x minus iy. Okay, there's the first starting point. I'll give you one more hint, and then I'll let you go, is that now we are going to combine these two fractions. So the left-hand fraction, I'm going to multiply top and bottom by x minus iy. The right-hand fraction, I'll multiply top and bottom by x plus iy. Okay, like I said, if you're feeling brave, hit pause there and see if you can manipulate this into looking like a circle equation. It actually does work. It's kind of cool. Okay, here we go. So if we expanded the brackets on the bottom, we conveniently have a difference of 2 squares and a complex number multiplying by its conjugate. So we're just going to get x squared take away I squared y squared, which is going to turn into x squared plus y squared. Okay, so now that the bases are both x squared plus y squared, we're going to combine the numerators. So we're going to do x minus iy, take away x plus iy, all in brackets. The right-hand side is still equal to I. We haven't touched that yet. Okay, on to the next step. We're going to simplify the top of the fraction. So we're going to have x take away x is nothing, and then minus iy take away iy is minus 2iy. Okay, cool. So we're on the right track because we have an x squared and a y squared. That's what we know circles look like. So we're getting closer. We just need to make it look more circular. So the confusing part here is that we have i's. But keep in mind that I is just a constant, and when you have a constant on both sides of an equation, you can just divide it away. So we can divide both sides by I, and now we have minus 2y over x squared plus y squared is equal to 1. Okay, I divided by I is just 1. Now we're looking good. We're going to multiply the x squared plus y squared across. So we have minus 2y is equal to x squared plus y squared. Looking very circular now, we'll bring the 2y across to make it positive 2y. So we have x squared plus y squared plus 2y is equal to 1. And now we'll just very quickly complete the square and make it look very, very circular. So we need to have a plus 1 after the y squared plus 2y. So I'm going to add plus 1 to both sides. And now we can factorize this as a perfect square. And then ta-da, we have a beautiful circle equation. We have a center at 0, minus 1, and we have a radius of 1. So what do you know? This weird looking thing right here is actually a beautiful circle. It's the poetry of mathematics, boys and girls. What a privilege. Okay, and finishing off with a challenging HSC question. This is from the 2017 HSC. It's considered a band 5 question. It's to do with vectors, okay? Also, there's a typo. They didn't put a space between S and A. Not good enough, Nessa. Okay, A, B, C, D are in the Argand diagram, and they represent A, B, C, D as points, okay? They form a square as shown, so all vectors are equal and they are all perpendicular. By using vectors or otherwise, show that C is equal to 1 plus ID minus IA. Okay, once again, if you're feeling brave, by all means hit pause and see if you can play around with this and make some vector equations to try and get something like this. If you want a hint to start you off, well, we're trying to find an expression for C and we're trying to use vectors. So the first thing I thought of is, well, if I have this vector right here and this vector right here, if I add them together, I'm going to get the vector from A to C. Okay, so see if you can find an expression for AB plus AD is equal to AC, like this. All right, if you're still watching, you've either given up or you've successfully done it. So let's see how we do it. So the vector from A to C. Remember, the way we calculate that is we do the point C, take away the point A. Okay, so vector from A to C is C minus A. AB is B minus A, and AD is D minus A. So we're starting to look something like this. We have a lowercase c, that's a good start. If we look at our target, what letter are we missing here? We have C, we have A, we have D. We don't have any B's in our target. So let's think now, how can I get rid of the B's in this equation? What relationship can I use? Well, the question very obviously said that it was a square, so we know that the vector AB is just the vector AD multiplied by I, as we've done a few times already today. Okay, so we're going to use the fact that vector AB is vector AD multiplied by I. So this bracket right here, B minus A, we can replace this with D minus A multiplied by I. And that's the massive key to this question. Now we just need to expand and simplify this, and it should hopefully look like this. So here we go, expanding it out, we get ID minus IA, we get D minus A. Conveniently, on both sides of the equation, we have minus A, so we can just add it to both sides and we have simplified. So we have C is equal to ID minus IA plus D. I'm going to rewrite this with two D terms grouped together, because then we can factor the D out of these two terms, leaving us with 1 and I. So we have C equals 1 plus I times D, take away IA, which is the target. And so the next step is the most important. We throw up a QED, we drop the mic, we got our 2 marks. We are a Band 5 student. Congratulations. Okay, hectic. So that's just to show you that there are some pretty gnarly HSC questions out there, but if you know the right tricks, you can eventually work your way through it. But we've got a whole year to get to this point, so if you're not there just yet, that's all good. Okay, a couple of exercises from Cambridge this week. So 1C is the Argand diagram stuff, which is a bit easier. 1E is the vectors exercise, which is probably a bit more challenging. So see how far through both those you can get, and let me know if you need any help. Thank you so much for watching. Catch you later.